Hello everyone, so today we're going to go over section 8.4, solving trigonometric equations using identities. So we are going to apply some of the trigonometric identities that we have seen in this unit in order to solve additional trigonometric equations, just as the title suggests. So let's look at example 1. We are to solve each equation over the domain from 0 to 2 pi. That means all of these questions will be in radians. Let's see what we have here. So in this first example, we have sine 2x minus cosine x is equal to 0. We are going to apply the identity for sine 2x, and that is, of course, equal to 2 sine x cosine x. And the cosine x and the second term is going to remain the same as before. Sorry about that. And it's going to be equal to 0. So notice that in these two terms, we have a common factor of cosine x, so we can factor that out. So we have cosine x multiplied by 2 sine x minus 1 is equal to 0. Which means either the first part, cosine x is equal to 0, or 2 sine x minus 1 is equal to 0. So the idea here is that cosine x is equal to 0 when x is equal to pi over 2 or 3 pi over 2. There's two possibilities. And then the second piece we have here is that sine x is going to be equal to 1/2. Right? We move the 1 to the right-hand side and then divide both sides by 2. And we know that sine x is positive in quadrant number 1 and also in quadrant number 2, and that the reference angle is pi over 6. So from there, we can determine that x is going to be equal to first pi over 6 in quadrant number 1, and also pi minus pi over 6, so 5 pi over 6 in quadrant number 2. Okay, let's move on to the second one. So this second example here, we have 2 cosine x plus 1 minus sine squared x is equal to 3. So it's a little bit more complex an example, but what we're going to do first is we're going to go ahead and rewrite 1 minus sine squared x as cosine square x using the Pythagorean identity. So this is simply cosine square x. So from there, what we have then is simply 2 cosine x plus cosine square x is equal to 3. Everything is in terms of cosine, so let's move everything to the left-hand side, and we have a kind of a quadratic in terms of cosine x, so cosine square x plus 2 cosine x minus 3 is going to be equal to 0. And we can factor this, of course, so we have two binomials. The first one is cosine x plus 3, and the second will be cosine x minus 1. And that's going to be equal to 0. Right, so the first part, we have cosine x plus 3 is equal to 0, which means that cosine x is equal to -3, and that's good because it has no solutions, right? We know that cosine x is between -1 and 1, so couldn't be -3 at all. On the other side, we have cosine x minus 1 is equal to 0, which means cosine x is equal to 1, and that only happens when x is equal to 0 or 2 pi. And that's it. So again, the idea is sometimes you want to use identities to make quadratic expressions like we have here, and other times we want to have a mixture of a sine and cosine. So no two questions are exactly alike, but generally we want to be factoring somehow. So notice the common theme between examples A and B is that we factored after applying an identity one time. So let's look at the third example here. tangent x plus cotangent x is equal to 2. This is a different example because for the first time we need to introduce a new element, and that is restrictions. So tangent x, of course, tangent x is equal to sine x over cosine x, so we know that cosine x cannot be equal to 0 from the first term. And then we also have cotangent x. Now cotangent x is cosine x over sine x, which means sine x also cannot be equal to 0 for this question. And of course, their combined restrictions would just be x cannot be equal to pi over 2n, where n is, once again, an integer. Okay, so that's the first thing, is to look at the restriction, if any apply. So in the previous two examples, there are no restriction because there is just sine and cosine, and there's no secant, cosecant, tangent, or cotangent, so there's no restrictions there. So for this question, what we can do is rewrite cotangent as 1 over tangent x. So here's what we have. We have tan x plus 1 over tangent x. Let's write it this way. So 1 over tangent x. And that's going to be equal to 2. So what we can do here is multiply every term by tangent x. So the whole entire expression, whole entire equation is to be multiplied by tangent x. So that will leave us with, the first term becomes tangent square x. Tangent x times tangent x. The second term becomes just 1, right? Because that's tangent x over tangent x is just 1. And we already dealt with the restrictions. And the right-hand side is going to be 2 times tangent x, so 2 tangent x on the right-hand side. From there, we can have a quadratic expression in terms of tan x, or tangent x. Let's move everything to the left-hand side. Tangent square x minus 2 tangent x plus 1 is equal to 0, which means we can factor this expression actually is a perfect square. So we actually just have tangent x minus 1 squared is equal to 0, which means that we only have to deal with tangent x minus 1 equals 0, which means tangent x is equal to 1. And tangent x is positive in quadrants 1 and 3. And we can also have the reference angle. The reference angle in this case is going to be pi over 4. Right? So tangent x is equal to sine x over cosine x, and is equal to 1 when sine x and cosine x are equal to each other, and that happens at the 45-degree angle. So the reference angle is pi over 4 in radians. So in quadrant 1, we have the answer pi over 4, and in quadrant 3, we have the answer pi plus pi over 4, which of course is 5 pi over 4. Okay, so those are the first 3 examples. Let's move on to the fourth example, just a couple more. So let's see here. Right, so we're introducing something new, and that is the idea of general solutions. So, and a kind of a different way of treating this double angle identity. So let's look at example 2a. It says cosine 2x is equal to cosine x. So we can rewrite cosine 2x as 2 cosine square x minus 1, and it's still going to be equal to cosine x on the right-hand side. From there, we can move everything to the left-hand side and have a quadratic expression in terms of cosine. So that is 2 cosine x minus cosine x minus 1 is equal to 0. This is, of course, factorable once again. And we can factor by grouping or some other method. It's entirely depends on the question. But once we factor, we have 2 cosine x plus 1. That's the first factor. And the second factor is going to be cosine x minus 1. Okay, so that means we have 2 binomials. The first one is, if it's equal to 0, then we have 2 cosine x plus 1 equals to 0. And the second one is going to be cosine x minus 1 is equal to 0. So either cosine x is equal to negative 1/2. That's the first possibility. Or the second possibility is that cosine x is just equal to 1. Now from here, we can look at the possibilities. Of course, cosine x is negative in quadrants 2 and 3. So this is quadrant 2, quadrant 3, and the reference angle is going to be pi over 3. So that leads us to, the first answer will be pi minus pi over 3, so 2 pi over 3. Sorry about that. And the second possibility, of course, is in quadrant 3, so pi plus pi over 3, which is 4 pi over 3. And on the other side, cosine x equals to 1 when just x equals to 0 or 2 pi. Right, so we found the solutions from 0 to 2 pi, but it does say to have general solutions. So for general solutions, we are to add just the period to each of the solutions. So in this case, it is simply going to be, the first solution is going to be x equals to 2 pi over 3 plus 2 pi n. The second solution is going to be 4 pi over 3 plus, again, 2 pi n. And also, of course, just 2 pi n for the answer here, the x equals 0 answer. And in all cases, n is an integer. And that's it. So there is another way to write the first two answers together, but this answer here is already quite sufficient. So let's move on to the last example of the day. And it's very similar to the one that we saw on the first page with the tangent and cotangent. So here we have sine x and cosecant x. And we're going to use the same thing, and that is multiply both sides by sine x. But before that, we have to take care of the restrictions, because we have cosecant x, which is, of course, equal to 1 over sine x. And that means sine x cannot be equal to 0 in this question, which means that x cannot be equal to integer multiples of pi or pi n, where n is once again an integer. Okay, so with that taken care of, we can multiply both sides now by sine x as planned. Okay, so the left-hand side will become 2 sine square x. The right-hand side will now be 7 sine x, and then minus 3. So again, we have a quadratic expression in terms of sine x. So let's move everything to the left-hand side. So we have 2 sine square x minus 7 sine x, and then plus 3. Again, this could be factored by grouping and by other ways as well, crisscross and so forth. But the factors, which is the important part, is 2 sine x minus 1, and then sine x minus 3. So we have two factors, just as we usually do for this kind of question. The first factor is going to be 2 sine x minus 1. We're going to set it equal to 0, which means sine x is equal to 1 over 2, or 1/2. And the second part is going to be sine x minus 3 is equal to 0, and sine x then is equal to 3, which, of course, as we know, produces no solutions, which is good. That makes the question a lot easier. Now we just have to deal with sine x is equal to 1/2. And as usual, we know that this is in quadrant number 1 and also quadrant number 2. And the reference angle is, once again, pi over 6. Okay, so from there, what we can do is to have the two answers. Number 1, pi over 6. And again, we're looking for the general solution, so we're going to add the period of 2 pi n to the solution. And the second solution is going to be 5 pi over 6. And we get that by subtracting pi over 6 from pi. So get into quadrant number 2. And again, add 2 pi n. And in both cases, n is once again an integer. So the last thing to do is, as always, check our solutions against the restrictions. But it looks like we're okay here. So that gives us an idea on how to apply some trigonometric identities to help us in solving trigonometric equations. In some cases, we have to use double angle identities. In some cases, just the fact that we have some reciprocal identities. So for example, cosecant x is equal to 1 over sine x. That could also be proved very useful. And so that's it for today. So once again, thank you for listening.